Hello and welcome, my dear friends. So, you must have gone through the notes of chapter 1, in which I had clearly explained what is the need of operating system in an embedded system product, and what are the types of operating systems used and what are the various features. So, by going through the notes, you must have understood each concept in detail, and specifically the concept of RTOS. So if we go through the topic 1, in which I have taken an example of 3 tasks of an operating system, rather in a real-time operating system, professional real-time operating system. So you can see we have created 3 tasks. One task as a metering task, another task LCD task, another task as communication task. So here by looking through the code, you must have understood the logic that how in an operating system, rather than real-time operating system, task concurrency takes place and how various tasks communicates with each other. So all the topics are self-explanatory. So let's go to the important topic, which is topic number 6. Topic number 6, which is an important topic for a beginner to understand, that what are the basic difference between a real-time operating system and a Linux operating system architecture. So in topic 1's example, we have used 3 tasks. So we will be taking that example here itself in order to explain. Okay friends, before going into the details of the differences of RTOS and Linux architecture, let us see what does real-time means in real-time operating system, which is well explained in topic 6 itself, that in real time the tasks and the ISR execution should be well deterministic in nature, means the time taken to execute a task should be known in advance. Let us try to understand with an analogy. Like, say for example, we enter into a metro station, takes a ticket and board the train. Now the total time travel, the price which we have paid for that ticket, the time with respect to that price is fixed. We have to get out of the metro station after a stipulated time, irrespective of the fact that we can change and various trains in our journey. Similarly, in a real-time operating system, when a task gets scheduled by the scheduler, the total time of execution should be known in advance, otherwise there will be failures. There could be failures. Now coming back to the our main topic, which was the difference between real-time operating system and a Linux architecture. The first difference exists onto the memory mapping. How the memory, or we can say RAM, is accessed or seized by real-time operating system, and how this RAM accessed and seized by the Linux architecture. So in order to explain this, I have taken the same example of topic 1, where we created some tasks, 3 tasks, but here I have shown only the 2 tasks out of that 3 tasks, the code for only 2 tasks. Say so this is what I have done. I have added some code to the original code of the while loop of the task metering and task communication. I have added some extra code in order to explain the difference, the fact. So you can see that this is a RAM, this is a complete RAM, this is a complete RAM, out of which this much portion is given to the stack and this much portion to the global area, data section and .bss. So the task metering, so this task can see the full memory can access, we can take a pointer, volatile pointer, and can access any section of the memory without any issues. Similarly, from communication task, we can use the volatile pointer and we can access any part of the memory. Also, the global variable, say we have created a global variable mysem and char x. So this global variable can also be accessed by this task and can also be accessed by this task. So there is no issues while accessing the global variables of a system by any tasks. Also, this is a function which can be accessed, which can be called by this task and this task without any issues. Now, which elaborates to the fact that in a real-time operating system, the global variables can be accessed by any task, the functions can be called by any task, but the task cannot access the local variables of another task. Now, say for example, this is a character pointer, which is a local variable to task metering. This pointer cannot be accessed by task communication. So there is a limitation only onto the stack sharing. We can also say that a real-time operating system is like a flat memory operating system. By saying flat memory operating system, it means each task interrupt handler sees the RAM as a flat space to them. They can access any part of the RAM, any task can access any part of the RAM, any task can access any memory mapped register of the peripherals. There is no as such protection among various tasks for accessing the RAM or the peripheral memory address registers. But this is not the case in Linux operating system. Linux operating system is totally designed in a protected manner. Okay, let's coming back to our notes, the topic 8, where in Linux we have explained that there are user space, kernel space. So this is the relation that we have a user process and the kernel services through a system call layer. So this is the architecture of the Linux operating system. So we will be seeing how the same concept of seeing a RAM is differs in Linux operating system in context of user space and kernel space. So this is in between the user space and kernel space, we have a system call layer. So it is well written here what are the many features of the system call. So in Linux, the user space and kernel space are used to protect the memory. User space applications cannot access the hardware memory or RAM, the kernel RAM, which is being protected. So if a user space application wants to access a device register of a peripheral, it takes use of system call layer, which sits in between user space and kernel space. So say let's take an example that there is a user space application running in Linux in the context of process, and we will going to learn the process and threads later in this chapter. Say and in this user space application, there we have used a hello world printf. This is a printf, which is a C library function. So the code of this C library function printf takes use of system call write. This is a system call write system call. So how this write system call transforms the control to the kernel so that the character gets print onto the hyperterminal or console is like this. So this is a system call layer. In this system call layer, the actual concept which is used is of software interrupt table. So in Linux, there is a software interrupt table of pointer to functions. Now say this is a write which is get mapped to sys underscore write. So when this write gets executed from a user space application, the kernel calls the system call interface layer, gets access to this software interrupt table and calls the sys underscore write function, which is actually written in the kernel space. Now the control goes from user space to kernel space using the system call layer with the use of the software interrupt table, and ultimately calls the put character. So we have seen that in Linux memory is protected, which is not in the case of RTOS. Any function, any task can access the memory of the system, but in Linux this memory is being protected from in context of user space and kernel space. So we will be going to see in detail how the memories and process and the threads in Linux will going to share the memory and pass the data from one context to another context. So let's create a sample C program which will use user space application to transform the variable to the kernel space.